Light is everywhere, illuminating our world, guiding us through darkness, and shaping how we see reality. But what exactly is light? Is it a wave, a particle, or something else entirely? For centuries, scientists and philosophers have debated its true nature, and their search for answers led to one of the most famous experiments in physics, the double-slit experiment. The double-slit experiment is simple in setup but profound in its implications. Imagine shining a beam of light at a barrier with two narrow slits, and then observing the pattern that appears on a screen behind it. If light were just particles, you'd expect to see two bright spots on the screen, matching the slits. But what actually appears is a series of bright and dark bands, an interference pattern, suggesting that light behaves like a wave, with the waves from each slit overlapping and interacting. This result shocked the scientific world. It showed that light can act as a wave, creating patterns that simple particles never could. But the mystery deepens when scientists tried sending single particles of light, photons, through the slits. The same interference pattern appeared over time, as if each photon somehow interfered with itself. The double-slit experiment revealed that light, and even matter, can behave as both a wave and a particle, depending on how we observe it. This strange duality is at the heart of quantum physics, challenging our understanding of reality itself. So, what is light? The double-slit experiment doesn't just ask the question, it forces us to rethink everything we thought we knew about the universe. And that's where our journey begins. In the 17th century, the nature of light was one of the greatest mysteries in science. Scientists and philosophers across Europe were fascinated by the question, what exactly is light? Is it something physical you can touch, or is it more like a ripple, invisible but powerful? At the time, there were two main competing theories about what light was made of, and these ideas would shape the future of physics for centuries to come. One of the most influential thinkers of the era was Isaac Newton, the legendary English physicist and mathematician. Newton proposed that light was made up of tiny solid particles, which he called corpuscles. To help people understand, he compared these corpuscles to small, fast-moving marbles. According to Newton, these light particles shot out from a source, like the sun or a candle, and traveled in perfectly straight lines. This idea made sense to many people because it explained some everyday observations. For example, when you hold your hand up to a lamp, you see a sharp, well-defined shadow. Newton argued that only tiny solid particles could create such crisp edges, because they would be blocked completely by an object, just like marbles hitting a wall. His theory also helped explain why light seemed to bounce or reflect off shiny surfaces, much like a ball bouncing off the ground. Newton's particle theory was powerful, and for a time it became the dominant way to think about light, but not everyone agreed with Newton. Across the English Channel, a brilliant Dutch scientist named Christian Huygens had a very different idea. Huygens believed that light was not made of particles at all, but was actually a wave, similar to the ripples you see when you toss a pebble into a pond. He noticed that waves have some very special properties. For example, when a wave encounters an obstacle, it can bend around it, a phenomenon called diffraction. Huygens argued that light could do the same thing, bending around corners and spreading out after passing through small openings. He also pointed out that waves can interfere with each other, creating patterns of brightness and darkness, just like overlapping ripples on water. This wave theory could explain certain strange effects that Newton's particle theory could not, such as the soft edges of shadows and the colorful patterns seen in thin films, like soap bubbles or oil on water. Huygens' wave theory was elegant and offered a new way to understand the behavior of light. So, which of these two great scientists was right? Was light made of tiny, solid particles, as Newton claimed, or was it a wave, as Huygens believed? For decades, scientists argued fiercely, performing experiments and debating in lecture halls and coffee houses. The truth, as it turned out, was far more mysterious and surprising than anyone could have imagined. As you'll soon discover, the real nature of light would challenge everything people thought they knew about the universe and open the door to a whole new world of science. In 1801, a brilliant English scientist named Thomas Young devised a clever experiment to settle the debate. This experiment, known as the double-slit experiment, would change our understanding of light forever. Imagine a thin sheet with two closely spaced slits cut into it. Now shine a beam of light directly at the slits. What do you think you'd see projected on a screen behind the slits? If you thought of two bright lines corresponding to the two slits, you're in good company. That's precisely what scientists expected based on the particle theory of light. If light were indeed made of tiny particles like Newton proposed, then those particles should pass through the slits in straight lines. This would create two distinct bright bands on the screen behind the slits, mimicking the shape of the slits. Seems logical, right? For centuries, scientists debated the true nature of light. Was it made of tiny particles, as Isaac Newton believed, or did it behave like a wave, as others suggested? This question puzzled some of the greatest minds in history. Then, in the early 1800s, a brilliant English scientist named Thomas Young set out to solve this mystery once and for all. He designed a simple yet ingenious experiment that would forever change our understanding of light. Young's experiment involved shining a beam of light through two very narrow, closely spaced slits onto a screen. What he observed would astonish the scientific world. Instead of seeing just two bright spots on the screen, as you might expect if light were made of particles, Young saw something far more complex and beautiful. The screen displayed a series of alternating bright and dark bands, stretching out like a barcode. This was not what anyone anticipated. The pattern was clear and unmistakable, and it demanded an explanation. Why would light, if it were made of particles, create such a pattern? The answer lay in the nature of waves. This remarkable pattern is called an interference pattern, and it's a signature feature of wave behavior. When two sets of waves overlap, they can combine in ways that either strengthen or weaken each other. In the case of light, the bright bands appear where the waves add together, and the dark bands show up where the waves cancel each other out. This was the first clear evidence that light could behave as a wave, not just as a stream of particles. To understand this, imagine a calm pond on a quiet day. Now picture yourself dropping two pebbles into the water at the same time, but at slightly different spots. Each pebble creates ripples that spread out in circles from the point where it hits the water. These ripples are just like waves of light spreading out from the slits in Young's experiment. As the ripples from each pebble travel outward, they eventually meet and interact with each other. Where the peaks of the waves from both pebbles line up, they combine to make a bigger wave. Where a peak from one ripple meets a dip from another, they cancel each other out, leaving the water flat at that spot. This is exactly what happens with light waves in the double slit experiment. Where the crests of two waves meet, they reinforce each other, creating a larger, more powerful wave. On the screen in Young's experiment, this shows up as a bright band, a place where the light is especially intense. These bright bands are the result of constructive interference, where the waves are perfectly in sync. But the story doesn't end there. Where the crest of one wave meets the trough of another, they cancel each other out completely. This is called destructive interference, and it creates the dark bands on the screen, places where the light seems to disappear. This interplay of bright and dark bands is a direct result of the wave-like nature of light, and it was Young's experiment that revealed this hidden side of light's personality to the world. The double slit experiment remains one of the most elegant and profound demonstrations in all of science, showing us that light is far more mysterious and fascinating than anyone had ever imagined. The double slit experiment showed that light, which was thought to be made of particles, could also behave like a wave. This mind-boggling discovery led to the development of the wave-particle duality theory, which states that light can exhibit both wave-like and particle-like properties. But the strangeness doesn't end there. Later experiments showed that not just light, but even matter particles like electrons exhibit this wave-particle duality. This means that the tiny particles that make up everything around us can also act like waves. The double slit experiment revolutionized our understanding of the universe. It forced us to abandon the classical Newtonian view of the world and embrace the bizarre yet fascinating world of quantum mechanics. This experiment laid the foundation for many groundbreaking technologies, including lasers, electron microscopes, and even the transistors that power our smartphones and computers. The double slit experiment opened a window into the quantum world, a realm governed by uncertainty and probability. In this strange world, particles don't follow the predictable rules of classical physics. Instead, they exist in a superposition of states, meaning they can be in multiple places or states at once until observed. The double slit experiment serves as a constant reminder that the universe is full of mysteries waiting to be uncovered. It teaches us to question our assumptions and embrace the unknown. The world, as it turns out, is far stranger and more wonderful than we could have ever